So let's say that we're going to be calculating a real world volume. Imagine that we have a bowl and we're trying to find the volume of this bowl. Now we know that what we have along here, let's say we know we want to have an outer radius of 10 centimeters and we want a base of 5 centimeters. And we want a pretty gradual slope to the bowl. So at the bottom, it's going to just be turning gently and not sharply. That helps it so that when you've got it filled with liquid, we've got a nice solid base. So if you're going to have a bowl that's this much wider on top than on the bottom, you want to have a nice gentle slope to it. So we want to figure out what expression we can use here and what height we have to capture a target volume in our bowl. Right? So we need a given height. So let's say our bowl is, well, let's say it is 12 centimeters tall. We're going to ask ourselves, what volume do we have in this nice curved bowl? And we need to figure out, what kind of expression are we going to have? Well, let's model our bowl here, because we can come up with a certain curve. I'm going to draw it like this so it matches the cylinders we have. We're going to have 12 centimeters this way. We can drop the centimeters and just use the numbers. We know with these numbers we are going to end up with centimeters cubed in the end. You want to find out what volume does this bowl have. Well, that volume is going to depend on how you get from one point to the other. Let's say this gentle sloping curve is the square root of x. Then the function that represents this is going to have to be some sort of proportion of that. So we're going to scale it by root x. That way, when we're starting here at 0, we get that very gentle slope, but it is going to taper off. We need to know, what scale do we need? So f of x is a root x plus 5. And what we know is that when x is 0, this works out to 5. When x is 12, this works out to 10 to catch us up at this part of the bowl. So that means our 5 here, we bring it across, we have 5 equals a root 12, or a is 5 divided by the square root of 12. We can rationalize that by recognizing that 12 has a perfect factor of 2, and then just multiply top and bottom by the square root of 3, so we have 5 root 3 over 6. This is the value that we're gunning for here. This is going to be our proportion in our bowl. So what volume would this bowl have? So the volume is the integral from a to b, which in this case is from 0 to 12, of pi f squared. So this is a root x plus 5 squared dx. Where again our a is 5 root 3 over 6. So then our volume, we could pull out the pi. We have from 0 to 12 of a squared x plus 5a root x times 2. So this ends up being a 10a plus 25 dx. So if we take this integral, we end up with a squared x over 2 plus, well, the integral of x to the half, we must have had a root x cubed before. this would have been multiplied by 3 over 2 when you took the derivative. So our 10 over a has to be multiplied by a 2 over 3, the reciprocal of that, plus 25x from 0 to 12. So our next step is to evaluate this at these points. Now remember, our a was 5 over root 12, or rationalized, that's 5 root 3 over 6. That means our a squared is 25 over 12. So up here, we have 25 over 12 times 2 times 12. So these are going to cancel. We are going to have here the 5 root 3 over 6 times 20 over 3. So 5 times 20 is 100. We have a root 3. We divide it by 6 and we get 18 times 12 cubed under the square root, plus 25 times 12, or 300, and then we subtract this when every term is 0. So I'm just going to save space and leave out that minus 0. So our v is pi times 25 over 2. Out here we're adding 300. The middle term is going to be the one that's a little bit tougher to simplify. So we know we have a 12 cubed. We could pull a 12 squared out to have just a 12 on the outside. Now that 12 simplifies with the 18 to make a 2 over 3. So that is a 200 root 3 over 3. Now that root 12 that we have left gives us another factor of 2 and another root 3. So this 3 cancels with these 3's, and we get 2 times 200, or 400. So our v then is pi times 25 over 2 plus 400 plus 300, or 700. Putting all of this over a single common denominator, we get 1425 pi over 2. Now this is going to be in cubic centimeters. So if we run this through our calculator to come up with an approximation of the value, we find that our bowl contains about 2,238.38 cubic centimeters, or it's roughly a 2.2 liter bowl. So this is a sizable bowl. Now the proportions we picked, a 10 centimeter radius, means it's 20 centimeters across the top. So not quite a full foot here. It's got a base that has a 10 centimeter diameter, and we've got a 12 centimeter height. So it is shorter than it is wide. This is probably something on the order of a small mixing bowl. But this is the general process. If we have some sort of physical object we need to represent, we can work this out and determine exactly what volume it contains. Now this does have another limitation and approximation here. You might notice that we've treated this bowl as though the material is infinitely thin. We've looked at just what it can hold. What we haven't now done is figure out, well, what volume of material would we need to contain this bowl? Right? If we're making it out of glass or plastic, how much glass or plastic do we need to physically construct a bowl so that it is 10 centimeter radius at the top It has our 5 centimeter radius at the bottom, and it is 12 centimeters high. So that is going to be the day 3 topic on volumes of revolution, is figuring out exactly how to represent this. With a shape this simple, where we have a uniform width, it's not going to be that difficult to do. In fact, the general idea is, if you want to make sure that this is always, say, 1 centimeter thick, to make it a nice sturdy mixing bowl, well, we are just going to redo it. Instead of going from 5 to 10, we add 1 that whole time. So instead of having an a root x plus 5, we add 1 centimeter. It gives us a root x plus 6. Repeat the integral. That gives us the volume of the outer sphere. Then we just need to add that 1 centimeter to the base. We need to add this volume, and we subtract the 2. So the concept is not that challenging, but some of the mechanics can be, depending on how things are going. For example, what happens if you don't want a uniform width for your material? So these are the kind of examples that we're going to be dealing with on day 3.